Good morning, everyone. Welcome to our virtual lecture. Today we are going to continue with chapter 6 and see how far we will go as far as chapter 6, electronic structure of an atom. Electronic structure of an atom. Please have a pen and a paper. Make sure you take or make your road notes as we progress with the lecture. So far, we have gone as far as section 6.5. Continue reading on chapter 6. Next week, next week will be midterm exam 2, which will cover only chapter 4 and 5. I'll send more information before the end of the week. What you need to have before the exam, what you need to know. It's going to be only chapter 4 and 5. I will make chapter 6 homework available. All right. If we get done today, I will make chapter 6 homework available for you so that you can continue working on that. We are almost getting to last month. Next week is July, and remember, our last day or the last day of the semester is July 31st. So take note of that. So far as the electronic structure of an atom is concerned, we went as far as looking at the mole or pores model of an atom, which use the emission, all right, line emission spectra to propose is model by uh, proposing that an atom, all right, an atom, let me share my screen here so that you can see what pores proposed in terms of model of an atom, model of an atom. What he proposed is that an atom just look like this. It's made up of the nucleus, and electron occupy what he called orbit, designated as N1, N2, N3, and so forth for energy level. How did he come up to this conclusion? He used line emission spectrum. We looked at how to, last time, we looked at how to find the energy difference between the two energy level or any given energy level using this equation, 2.18 times 10 raised to negative 18 over 1 over n final square minus 1 over n initial square. This is the equation used to find the energy difference between uh, energy levels in pores model of an atom, that are energy level 1, energy level 2, where the electron is tending to. It was proved and it was established that light behave as matter, all right? Light behave as matter. And de Broglie came up with his theory that if Broglie, all right, de Broglie reasoned that if light behave as matter, and then matter can behave as light, and we can calculate what we call de Broglie wave of any matter. We call this de Broglie wavelength, and it is given by the Planck's constant of mass times velocity. And remember, meters per velocity or speed has to be in meters per second, and mass has to be in kilogram. Remember to change the mass, convert to respective unit. He was reasoning that if light behave as matter, and then matter can behave as what? As light, it has a wave property. We can calculate the wavelength. This is called the de Broglie wavelength. You see question saying that what is the de Broglie wavelength of de Broglie wavelength of any substance? Now, with that, it is now the model of an atom changes the equation that electrons travel around the nucleus following a wave or with a wave pattern that electron behave like a wave. It's not going in a straight pattern, but it's going around the nucleus in a wave of manner. Where we stopped is the Heisenberg uncertainty. He came up and said, all right, if electrons are moving around the nucleus, all right, if electrons are moving around the nucleus in a wave pattern, there is no way we can know both the position and the speed of the electron, and this is called the de Broglie or uncertainty principle. Uncertainty principle, which is state that it is not possible to know both the position and the speed of matter. We call this uncertainty principle. That it is not possible to know the exact location of an electron in an atom and at the same time know its speed at which it is revolving around the nucleus. This is what he proposed. We call this uh, Heisenberg uncertainty principle, and this stands for uncertainty in position, and this stands for uncertainty in momentum. This equation, I want to just rewrite this. This is more straightforward, that you multiply the mass in kg times the uncertainty in velocity greater or equals to the Planck's constant over 4 pi over 4 pi. This is called the uncertainty in velocity, and this is the uncertainty in position. This is the uncertainty in what? In position. And what is this principle is all about? It is coming in with the electron concept that, all right, if Bohr is suggesting this is the electronic structure of an atom, how comes that, or it's not possible to know the exact position and the exact velocity, If you are asked to find the uncertainty in position of any matter or any object, all you have to do is use mass to make whatever you are looking the subject of the formula, For example, uncertainty in position, which is x, is greater or equals to the Planck's constant of 4 pi, you know the numerical value for pi, times the mass times uncertainty in velocity, If you are looking for uncertainty in position or in velocity, sorry, this is greater or equals. It's not equals. Based on what we have here, it is greater or equals to Planck's constant of the pi, 4 pi times, all right, times the uncertainty in position, which is x, times the mass in kg, This is the Planck's constant we saw earlier on. This is 6.626 times 10 raised to 34. And this is always mass in what? Mass in kg in kilogram, mass in kilogram. And this is the velocity or speed in, it is a speed in meters per second. This is velocity or speed in meters per second. You need to change that before you plug in the equation. So this is talk 2. still trying to come up with the model of an atom. Everybody is coming up with ideas, and uncertainty principle has to do with the electrons in an atom, and he came up with this. Heisenberg came up with this principle. Which two things can be asked, either in position, the uncertainty in position, or velocity. This is one of the equation or one of the work example we looked at last time. Using Heisenberg uncertainty principle, calculate the, all right, calculate the uncertainty in position of 1.50 milligram of mosquito moving at 1.40 meters per second if the speed is known within plus or minus 0.01 meter. This is the uncertainty in position. We care less about the velocity. Don't plug in this equation and think that you will get the answer. So for this, we'll just have to say the uncertainty in position, all right, x is greater or equals to the Planck's constant over 4 pi times mass times the uncertainty in velocity. Planck's constant is the same value. I'll give you this in the exam. If it is homework, you have to use the text and plug in the numerical value for Planck's constant. This is times 10 to negative 34 joules per second over 4. Pi is the numerical value, you know that, 3.14 times, all right, mass, changing this to kilogram. Gotta change that to kilogram, 1.50 times 10 raised to negative 6. Why negative 6? We're changing this to kilogram times the speed, all right, or velocity. Uncertainty in velocity is 0.01 meters per second. Uncertainty in velocity. It is not the velocity here. It's not the uncertainty is what we are looking at, not the speed, not the velocity. So that the kilogram right here will just go the second. This will, if you plug in the equation, this will be greater than or equals to. If you plug in your equation, plug it in the calculator, this should give you 4 times 10 raised to negative 27 meter, negative 27 meter. Please double check that. Make sure you get the correct value. That is the uncertainty in position for the mosquito. All right. Know your calculator. I'll allow you. Jennifer last time requested that your calculator you work more efficiently, or it's simplest to work with your calculator than the lockdown browser calculator. So allow you to use your calculator in this kind of problems. So for this, I want you to try this and see what you will get for that. I know you are wondering, how did we end up with one there? This has one significant figure. You're gonna change that to one significant figure because of the uncertainty in principle. You will do the same thing for this problem. Make sure that you get this is 6 times 10 raised to negative 8 meter. For second problem, this problem, make sure you get this. If not, let me know. In this case, the uncertainty in velocity is 0.01. It's the same thing as the one we had, but this time round time is 10 raised to negative positive 5 meters. This is the uncertainty in velocity. It's the same setup as the one we had here, except what you will change is this term right here with the numerical value I gave you here, because we have been given that the speed is 3.0 plus or minus 0.01 times 10 to positive 5. This is the uncertainty we are going to use, and this is the value you're going to use, and make sure you express in one significant figure because of that. Pay attention to the uncertainty part, okay? What you will see commonly in uncertainty principle, it could be an electron moving around the nucleus, and you got to know the mass of an electron in kilogram. Mass of a proton, mass of a neutron. Might not be straightforward, but the mass of an electron, mass of electron is 9.109 times 10 raised to negative 31 kg. If you are doing homework assignment, you see something along this, along to the effect that you got to find the uncertainty in an electron moving around the nucleus. Probably they expect you to know the mass of an electron. This is the mass of an electron. In an exam, I'll give you that. Mass of a proton, all right, proton are positively charged. This is 1.675 times 10 raised to what? 10 raised to times 10 raised to negative 27 kg, 27 kg kilogram. This is the mass of a proton and a neutron. I saw a question at the end of the chapter problems along the neutron, and this is 1.673 times 10 raised to negative 27. Other substances you may be given, all right, if it is a track-based pole or soccer pole, you will be given their mass. So you have to make sure you change the mass to kg, change the mass to kg in this equation. That's why. And this speed has to be in kilogram. Any question on uncertainty principle? Any question on uncertainty principle? Heisenberg uncertainty principle? All right, if that, let's move on to section 6.5, which is the current model of an atom. Current model of an atom, where we are as far as the picture, we call it quantum mechanical model of an atom. Based on uncertainty principle, we know we cannot find the exact location of an electron and at the same time know the speed. It's not possible based on what we just took. However, an Austrian physicist by the name Schrödinger or Schrödinger, whatever the name is, Ewin, he came up with a principle and developed a mathematical equation which we can precisely determine the location of an electron in an atom. I will not go into the wave or quantum mechanics in details, but I'll just mention or just bring to your attention what it's all about. In this mathematical, all right, he developed what we call wave. This is called wave equation. Wave equation, of which in this mathematical treatment, we can know both the nature, that is the wave, and exact location of an atom, which in this course, we call it orbital. This is the wave square. We call this wave wave function, all right? solution of wave equation is called a wave function, and a solution is basically an orbital, which is defined as the region of space where there is likelihood of finding an electron. You can call this orbital, all right? Orbital wave function. You see in this illustration, there is a dense region, or there is, you see these are dots. As you move away, the number of dots decrease, which means the probability of finding an electron in this region of an atom is almost zero. You're not gonna find, but at a certain region within an atom, there is high probability of finding an electron within this region. We call this the wave function. We're gonna look at it. Wave function is simply the region where we can find an electron, and we will call this an orbital, all right? Region of space where there is likelihood of finding an electron, all right? A solution of wave equation is called wave function, and we can find an electron. So this stands for region where there is likelihood of finding an electron at any given time. There is high chance of locating an electron. The square of the wave function, if this is the wave equation, we call this an orbital. We're not going to solve that, but the orbital here are defined by the what we call quantum number. Solving the wave equation yield numbers, we call it quantum numbers. Just like the physical address where we live, all right? The numbers describe the region where there is likelihood of finding an electron. So in the previous course you took, you just said that electron configuration, but you didn't know how to use the quantum numbers. Quantum numbers are a solution of this wave function. It describes the region within an atom where there is likelihood of finding an electron. Remember what I said earlier on, orbit versus orbital. An orbit is just circular path around an object. We call this orbit. But orbital is a region within an atom. We have high probability of finding an electron. Each orbital is described region where we can find an electron. Orbital is described by three quantum numbers. What are the three quantum numbers we're going to talk about? In fact, there are four. We're going to talk about four, but let's look at the three numbers used to describe an orbital. First is the principal quantum number, and it corresponds to the Paul's energy level. Remember, energy level 1, energy level 2, energy level 3. We call this principal quantum number, and we designate using the letter n for n equals to 1, n equals to 2, n equals to what? N equals to 3. Energy level 1, energy level 2, energy level 3. We call these principal quantum numbers. And it take numbers, n could be 1, 2, 3, 4, all the way. Take whole numbers, n equals to 1, n equals to 2, n equals to 3, n equals to 4, and it describes the energy level on which orbital reside. It does not describe an orbital, but it's just the energy level. So principal quantum number n represent energy level. Underline the word energy level because other quantum numbers represent something different. Numbers from 1, it cannot have 0. 0, non-existent. So it takes 1, 2, 3, all the way to infinity. Anything greater than 1 or greater than 1, it cannot be 0. So it corresponds to Bohr's quantum Bohr's model, energy level 1, energy level 2, energy level 3. Remember, we are giving an address to an orbital. First, these energy levels represent the shell where orbitals reside. So we have orbitals in shell number 1, we have orbitals in shell number 2, we have orbitals in shell number 3. Think of it as first floor, second floor, or third floor. In first floor, we have rooms where people live. Second floor, we have rooms. So I'm using rooms as orbitals and floors as shell. Shell number 1, shell number 2, and they just represent the Bohr's model. And then there is the angular momentum. Angular momentum quantum number is designated using letter L. And what does quantum angular momentum quantum number represent? This represents the shape of the orbital. You may recall the spherical, we're gonna talk about that, the dumbbell. This quantum number represents the shape of the orbital, and it takes this value, n equals to, take 0 all the way to n minus 1. So we start by looking at the n first, and then you go L. You build those quantum numbers based on principal quantum number, which is the n. And then the values run from 0 all to n minus 1. So if n equals to 3, let me give you what that means. If n equals to 3, possible, all right, possible values of L will be 0, 1, and 2. It cannot be 3 because the allowed values here are what? 0 all to n minus 1. Allowed values are 0 all the way to n minus 1. If L equals to 1, no, or n equals to 1, and then L could have only 0 because, it takes values n to what? N 0 to n minus 1. So if n is equals to 1, 1 minus 1 is 0. So we only have one possible value for. How about if n equals to 2? Then possible values for L will be 0 and 1 because of what? Because n minus 1, which is 2 minus 1 is 1. These are the possible values for L. If n equals to 4, I know I work 3, possible values for L will be 0, 1, 2, and 3, because we cannot have 4 because the maximum values, all right, ranges from 0 to n minus 1. If n equals to 5, then possible values for L will be 0, 1, 2, and 3, 4. It cannot have 5. It cannot have 5. It only goes all the way to n minus 1. That is the allowed values within the energy level. That means this is energy level 1, energy level 2, energy level 4, energy level 5. And that is how you look at the possible values for L, which is the principle, which is the quantum momentum, quantum, all right, angular momentum quantum number L, and it describes the shape of what? The shape of an orbital, the shape of an orbital. Those are the allowed values for L, and you are familiar with these letters in electron configuration, SPDF, SPDF. These are the letters used for describing the angular momentum quantum number L. If L is 0, and then this is the letter used. P, if 2, D, and F is 3. These are the letters and these are the values. We designate these values using the letters S, P, D, and F. And this has to do, by the way, this has to do with the line emission spectrum, that they were sharp, pattern, diffuse, and so forth. This has to do with the line spectrum we talked about earlier on. And whoever kept these letters had to do with those line spectrum, and they follow each other in that sequence. So we will use that. Now, M's of L, or magnetic quantum number, these are read as M's of L. You read this as M's of L, M of L, subscript L. It detects values. This describes, first of all, the three-dimensional orientation of orbital within the space. This is the orientation. Remember principle? Describe the energy level or represent the energy level. Angular momentum describe the shape, and this one describes the orientation in 3D space of the orbital. What are the values for L? It detects values for L, M's of L, values of M's of L, take or lie between L all the way to positive L. It sounds abstract, but with practice, you'll understand what is going on. I will show you how you designate these or assign the values for N. If let's start off with L, if N equals to 2, and L equals to, remember, L can be 0, it can be 1, right? Because L take values from 0 all the way to N minus 1. So if I pick this, then my M's of L will be negative 1, 0, and 1. M's of L, it takes values from negative L to positive L, negative L to positive L, depending on what value you pick. If I pick N equals to 2 and my L equals to 0, and then M's of L will be 0, because from negative 0 to, we don't have negative 0, it's just 0 and 0. Negative 1 to positive 1. Let me pick another energy level or 3. Let's say N energy level 3 is, that's energy level 3, shell number 3. We know possible values for L can be 0, can be 1 to N minus 1, which is 2. If we just use this and this to find M's of L, if N equals to 3, L equals to 2, M's of L will be -2, -1, 0, 1, all right, and what? And positive what? And positive 2. It detects values negative L to positive L. That's how you look at or assign the values of L based on the numerical value for L. If we just say N equals to 3 and L equals to 1, and then M's of L equals to, I didn't mean to, it's a subscript. It's a subscript. So it's going to be M's of L like that. This will be -1, 0, and +1. These are the possible values for what? For M's of L. M's of L. And if n equals to 3, L equals to 0, and then our M's of L will be charged 0 in that case, because -0 to 0. So it depends on the value for L. When you say allowed values of M's of L are integers ranging from -L to +L, it depends. You start with N first, and then you come to possible values for L and pick or depending on what you are dealing with in L, the values of L is anchored on the value for what? For L. M's of L is anchored on the value for L. Angular momentum, all right? It represents the 3D. And remember what we said earlier on, what they represent. You got to know what that means. So these are the three quantum numbers which describes an orbital. An orbital is a region within an atom where there is high probability of finding an electron. And we use quantum numbers to describe the location. Remember Heisenberg saying, no, it's not possible to really know where the electrons are. At the same time, know the speed. But Schrödinger came up with a wave equation, which when we solve the wave equation, we end up with what we call it's a solution for wave equation at the orbitals. We call wave function, wave equation, the maker. So these are the three quantum numbers. I want you to understand that they represent or they describe an orbital where we can find an electron. N, energy level, L, all right, the shape, all right, and it ranges from 0 to n-1, and the possible values for M's of L, which describe the three-dimensional orientation on the space or of an orbital, take values n or L to negative L to positive L, positive L, negative to positive L. Therefore, any given energy level, there can be up to 1s orbital, 3p orbital, 5d orbital, 7f orbitals, all right? So when we say 5d orbital, what does that mean? 3p orbitals. Let me just back up to where I was. If you remember, all right, if you remember SP, this is 0, 1, 2, and 3 here. There is S, P, and D. All right. D has, if you look at these 5, D is 2. So it takes values 1, look at this, 1, 2, 3, 4, 5. For any D, for where you have D here, you should have 5 what? 5 orbitals where you can find an electron. There is this. Where you have an F3 here, let's see, for F, n equals to 4. L could be 1, no, 0, 1, 2, 3. Let's see 3 here. M's of L will be -3, -2, negative what? Negative 1, 0, 1, 2, and 3. These are the possible values. 7, 1, 2, 3, 4, 5, 6, and 7. That's what is meant by here, 7 F orbitals. You may recall, and this is where we are going, that, where you write the electron configuration. Remember when they used to use these dashes? These are represent orbitals where we put the electron. We are going to electron configuration later on. So 5 here, if 3F, we have 7 orbitals. 7 orbitals. If it is 2, we have 5 orbitals. If it is 3, we have 3 orbitals. You have seen this. If it is 2p, you may have seen somewhere with 1, 2, 3. This is an orbital. If it is 3p, we have 1, 2, 3. These are orbitals. We're going to use those when we write the electron. I just wanted to explain this last bullet point. What do they mean by at any given energy level, there can be 3p orbitals, 5d orbitals, and so forth. Orbital regional space where we can find an electron, So orbitals with the same value, all right, n value, represent the electron shell. Orbitals with the same value of n form an electron shell, shell number 1, shell number 2. So here, these are orbitals with the same n value. So this is an orbital, this is an orbital, this is an orbital. Shell number 2, shell number 3. And different types of orbital within the shell, they exist within the same shell, such as 2p, 2s. These are subshell. So we may have 2p, 2s, and 2p. This is a subshell, and this is another subshell. Energy level 2 has 2 subshell. Energy level 3 has 3 subshell, and so forth. Look at table 6.2. It summarizes the 3 quantum numbers we have seen so far. N stand for energy level 1, energy level 3, energy level 4. And the possible values for L, angular momentum, and their designation. Possible values for M's of L, all right? So if if L is 1, M's of L will be positive 1 all the way to negative 1. And total number of total number of orbitals within a shell. Total number of orbitals within a shell here. This is where we use this. You may use total, this total number of orbitals. Shell, or sometimes this is energy, energy level. Energy level is given by 2, no, it's given by n. This is n square, where n represent the number of electrons. Let's see, n is equals to 1, then the maximum number of orbital is 1, because 1 square is 1. If we come to energy level 2, the number of orbitals is 2 square equals to 4. It works for energy level 3 as well. If we want to know the number of orbitals in energy level 3, 3 square is 9. Energy level 4, 4 square is 16. That's how you find the total number of orbitals within the shell, within the energy level. All right? This is just the subshells, but this is the total number of shells within the shell number, You can, all right, we'll come back to this when we want to find the number of electron. We haven't get there. Let's see if you understood what quantum numbers and how to figure out the quantum numbers in an atom. What is the learning check? Look at the PowerPoint slide. What is the possible values of L if n equals to 4? Is it A, 4? Is it B, 0, 1, or 3? Remember, I'm talking about possible values of L. C, -3, -3, -2, I guess I meant to say, or 4, or D. How will you figure it out that? You should, yes, thank you. Garcia, that is correct. That is correct. Possible values of L. Look, you say if n is equals to 4, L can take values 0, 1 to n minus what? N minus 1, which is 3. It cannot go all the way to 4. Those are the possible values, all right? And then from here, depending on which sub-level you pick, if n, let's see, if L is this, m's of L will be -1, 0, and 1. Remember, positive to negative. If it is 2 like that, and then m's of L is -2, -1, negative, no, not negative, this is 0. I meant to say it is 0, +1, and +2. These are possible values. And if L is 3, then m's of L will be +3. No, not positive, but negative. I always like to start with negative. So I'm going to start with -3, -2, -1, 0, 1, 2, and 3. This is how you look at it, because you can be asked either way that which one is of the following quantum numbers are correct, and you're given a wrong value for m's of L. So n can be 4, m's of L can take any of these L can take any of these values, and then m's of L can take any of these values you see here, depending on. You pick the value for m's of L. Once you figure it out, the value for L, all right, always you'll be given that, and the correct answer is B. Anyone with question? Good. Now, how many different values of m's of L how many values of m's of L are possible in 5F? 5S in and FS in front. What are the possible values for m's of L for 5L? You see, for this question, yes, correct, David, correct. For this question, you may want to have this, that it take possible values, like you say this is the value, all right? How will you enter that? And then here is the letter. Remember 0, 1, 2, 3, 4, and then S, P, D, F, G. There is H, 5, there is H, but we don't need that. This one now represent the letters. We are talking about the 5F. And these are the letters. Remember, this is for L, all right? L values. These are L values. And if we are talking about 5F, that means L is equals to 3. L is equals to 3. And M's of L take values negative L all the way to positive L. And -3, -2, -1, 0, 1, 2, and 3. That's how we ended up with 7 B. Somebody might be wondering, how did we end up? Do I have to memorize? 1, 2, 3, 4, 5, and 6, and 7. And these are the orbitals. These are the orbitals. That's how you figure it out. Suppose you are given something else. How will you approach that? These are the possible values for L. And these are the letters. We are given 5F. So 5F, I know this letter, its value is 3. And if I know L is equals to 3, M's of L take values negative L to positive L. And that is how we end up with different possible values. I've seen question along, it can be twisted that which one of the following is not a possible value for L when given this. I can give you any of these numbers and then give you maybe positive 4, for example. Which one is not possible? And say, somebody will say, oh, maybe it is positive 4 because 4 is within. No, no, no. You have to be well-rounded. What happened to 5? Thank you. That's why we are here. What happened to 5? Antonio, 5. It has to do with, all right? This tells us that 5 is the energy level. All right, 5F. It is energy level 5. It can be even 4F. We don't have 2F, based on the electronic structure. So 5 is just the energy level. It doesn't tell us anything. So if I pack up to that, let me just use this. I can say if n is equals to, let me show you where 5 comes in, or what is the role of 5 in this question. And maybe, oh, you got it. All right, yeah. So this means n is equals to 5, and L could be 0, 1, 2, 3 to 4. Remember, possible values of L goes all the way to n minus 5. And then M's of L now depend on what you are looking for in terms of, if you pick this, if you pick this, if you pick that, if you pick that, if you pick that, if you pick that. Got it. All right, let's move on. So that is what all about M's of values, electronic structure. And what are these values? They describe the orbital, which is the region of space where we can find an electron. Here comes a question again on quantum numbers. The dash quantum number defines the shape of an orbital. Is it spin? We haven't talked about the spin. Magnetic principle, angular momentum, or psi? I don't even know. Sometimes they give you questions or terms you have never seen. At that point, you may use elimination method. Elimination method. The spin, we will talk about that momentarily. Magnetic, Antonio say D. Yes, you're right. Somebody say B. B, I'm gonna pack up, show you what it means. Let's see, somebody say that it is quantum. Let's see, this is the quantum magnetic describe the three dimension, the orientation in 3D space. So quantum or magnetic quantum, and then there is the angular momentum quantum, which describes the shape momentum. So for this one, you have to know it is D, magnetic quantum, describe the orientation. You will see a question on energy. Principal quantum number represent energy. This is energy level 1, energy level 2, energy level 3 as you go away. The higher the number it is, the higher the energy is. Okay? So know the, all right, know what those three quantum numbers represent. We'll come back to spin quantum number momentarily, all right? There are dash orbitals in the third, all right? There are dash orbitals in the third shell. Shell is the same as energy level. Shell number 1, shell number 2, shell number 3. Is it 25? Is it 4? Is it 9? Is it 16? Or is it 1? How many orbitals are in? How many orbitals are in the principal quantum number 3? How will you figure it out that? What are orbitals? Yes, thank you, David. It is C. Number of orbitals. Remember, in my notes here, I think it's right here. Total number of orbitals in a shell or energy level is given by n squared. And I gave you energy level 2. So for energy level 3, we will say 3 square, and this is 9 orbitals, 9 orbitals. And these are 4 orbitals. So for any orbital, I can just plug in this equation and it will give you the total number of orbitals. So for that energy level or shell, it is 3 square, which is 9. 3 square, which is 9. Good. So if you are given any other energy level, just use this equation and you will get the number of orbitals, which is regional space where there is likelihood of finding an electron. Likelihood of finding an electron. Representation of electrons, orbitals. We have a spherical, which is the S. Electron density, S orbitals are always spherical. I know you know this from introduction to chemistry, and it has a value S, that's a value 0. For orbital, they are spherical in shape. Remember, spherical and dumbbell. For S, they are spherical. And the higher the n value, they get larger as the n value increase. Look at this, 1s, 2s, 3s, even 4s will be larger than 3s, and 5s will be larger than all of them. So as n get larger, the radius of the s orbital keeps increasing. That's what you need to know. And they are spherical in what? They are spherical in shape. For n, as that is the energy level, the number of nodes, that means where there is 0 probability of electrons corresponds to n minus 1. That means if you look at this plot right here, for energy level 1, you don't see any node. Node is where, or depression, you see this is a node. That means no probability of finding an electron here. No probability of finding an electron here. No probability of finding an electron here. How do you know how many nodes? I've seen question asking you to draw the, uh, the probability of finding an electron in 1s, since 1 minus 1 is 0, there is no node. N equals to 2, so that means n 2 minus 1, we have only one node for 1s. And then 3s, all right, 3 minus 1, we have two nodes. And if you look at the peaks, it is getting larger as you go from, as you go away from the nucleus, distant from the nucleus, distant from the nucleus. That is something you need to pay attention what they represent. And sometimes you may be given in multiple choice and say, which one of the following diagram represent 2s? And you don't see anything. I will use the nodes to tell me. And the picks, for example, I don't expect to see two nodes on 2s, nor do I expect to see any node on 1s. All right. So that is the nodes and the probabilities with the increase. 2p, they are dumbbell, all right, two loops facing each other depending on the direction. You may have seen something like 2px, 2py, and 2pz. It represents the orientation on 3D. This is 2pz, lying along the C plane. 2p X, that means it's lying on the x-axis, it's lying on the y-axis. You see this notation, and at any given point, an electron can be anywhere. It's like putting a fly here. A fly can go anywhere. It can be here at one point, this at that point. This is the shape of the any p orbital. It could be 3p, it could be 4p, 5p, and so forth. There are two look like two loops. We call this dumbbell. This is the d orbitals, look like four loops, and just the way we talked about, it represent 2 or 3D, 4D, depending on which plane they lie. They are designated as YC, it is on the Y, and it's on the Z axis. When you get to the four orbitals, it gets complicated, and rarely will you see anything on 4D. Just pay attention to the shapes of the 2p, all right? Not 2p, but the p orbitals, the s orbitals, and possibly maybe d orbitals. All right, let's see. Somebody has a question here. Oh yeah, you're answering dash orbital are spherical. Yes, it's easy. Yes, correct. It is. You may see in the exam dumbbell. All right. You have to know what they represent just to give you an idea of what it is. Now, let's go back to hydrogen atom, and with respect to orbitals now, for one electron system, hydrogen orbitals on the same energy level have the same energy. This is energy level 1, energy level 2, energy level 3. It might be something like this. I've used this over and over. 1, 2, and 3. As you go away from the nucleus, we say this is energy level 1, represented by this box right here. This is an orbital, n equals to 1, n equals to 2, n equals to 3. And if you look at the boxes here, they represent subshell. This is subshell, 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 subshell. And this is right here, n equals to 1, n equals to 2, n equals to 3. I know you know that. But I want you to take note of this. With what we have on this PowerPoint slide here, number of subshell equals to the shell what? Shell number. Shell number one has one subshell. Shell number two has two subshells, the 2s and the 2p. Shell number three, we have three subshells, 3s. Shell number four, we have four subshells. Shell number five, we have five subshells. This is what is what's happening with the subshells. We call this degenerate. What do we mean by degenerate orbitals or degenerate orbitals? Degenerate orbitals, that means they have the same energy. These are degenerate orbitals. They have what? Same energy. You'll see later on orbitals which are not degenerate. For multi-electron, that means anything with more than one electron. The previous one was for hydrogen. If we go to helium on the periodic table or any other element on the periodic table, we consider those as multi-electron atoms. And energies of orbital are not the same. They are not degenerate. If you look at the energy level 2, all right, for multi-electron, the energy in energy level 2, 2p and 2s, 2p has slightly more energy than 1s, or I mean 2s. When we get to 3 or energy level 3 here, 3s and 3p's orbital, 3p are slightly higher in energy than 3s. Likewise for 4s and 3d. There is an overlap here, by the way. It should be coming back to you, those who can recall the electron configuration. There's what we call overlap. Quite often when we get to electron configuration and so you're asked to write the electron configuration, somebody will think that let me just put in or put electron in the 4Ds or get down with the 3Ps or 3Ds, and doesn't follow that pattern. Energy-wise, electrons will occupy 4s before occupying the 3d. We call this overlap, and it has to do with the energy. Just like if we have a skyscraper, 110 floors going up, and no escalator, no elevator. Always you have to take your groceries all the way to 110. If you are looking for an apartment, it makes sense that maybe you'll take like third floor or second floor. Why will you always taking stairs all the way to 110, right? So you will occupy the lowest. In terms of energy level, also electrons occupy the lower, occupies orbitals with lower energy. There is an overlap. Multi-electron, they do not have degenerate. When we say degenerate, that means they have energy. These 2s and 2p, they are not degenerate, but here, these three orbitals, they are degenerate. These are degenerate, but 3s and 3p, they are not degenerate. Orbitals set in the same sublevel are said to be degenerate. Yes, the 3Ds here, 1, 2, 3, 4, 5, each box in here represent an orbital, and we say they are degenerate. In 3p here, all right, 3p, 1, 2, 3 have 3 orbitals, and they are said to be degenerate. They are said to be degenerate orbitals. That means they have same energy. If you look at 4s and 3d, there is an overlap, and this has to do with energy. When we get to higher energy level, you will see even greater overlap in subshell shell and orbitals, and nothing else, but it has to do with energy. Before we look at the electron configuration, any question on degenerate, you got to know what degenerate orbitals mean. That means they have the energy, same energy, and there is overlap. Now, the fourth quantum number here for an electron we call m of s, and they represent the spin of an electron within an orbital. All right, Anthony, how do you know if they are degenerate? Yes, how do you know whether they are degenerate? It's just gonna fall in the right place because of, let me go back here and show you how do you know they are degenerate. You know they are degenerate because if you write the electron config, we can come back to that. If we say 2p, in p sublabel, we have 3 orbitals and we say they are degenerate. For 2s, they cannot be degenerate with the 2p's. I will know by their designation. 3s and 3p cannot have. At the outset, this is something you need to, all right? You need to know that when you write, let me just jump again for a minute. 1s, we're gonna come back to this. 2s, 2p, 3s, 3b. Remember, we have 3 orbitals here. We have 3 orbitals there. All the peace orbitals are degenerate. All the 3 Ds, they are degenerate. If they are within the same subshell, we say they are degenerate. Orbitals within the same subshell are degenerate. That's the only way you need to know that. How will I know that these are degenerate? These are the orbitals within the same subshell. These are the orbitals within the subshell. They are degenerate. So you cannot have a 4p and a 3d having the same energy. They are not. They are in different subshell, and therefore they are not degenerate. So the word degenerate, it can just fall in the right place, that they are the same subshell and they are said to be degenerate. All right, thank you, Anthony. So that is how you will know that they are degenerate. It's just, that is what it is. All right. So 2s, 2p, so you know what this means. Once we get to electron configuration, you may see that what means. So I was here on the spin quantum number. Electrons occupying the, occupying the same orbitals have, or they spin in different direction. Let me just bring what you may have seen before. Remember this. Do you remember this? We're gonna call this. Do you remember this notation in writing electron configuration? Kenneth, you remember that? Anybody else? Do you remember that? We're gonna come back to that. There's something I want to say here. Anybody remember that? If you don't remember, don't worry. Yes, Anthony, you remember that. All right, we're gonna come back to this. The reason why I'm bringing that is, or you didn't know why you had to put these 2 arrows facing in opposite direction, is because of the 4th quantum number in describing an orbital. Remember earlier on I say a dash represents an orbital where we can find an electron. And 2 electrons occupying the same orbital, all right, have opposite spin. They spin in opposite direction. In opposite direction. All right, 2 electrons. Look at this. 2 electrons in the same orbital do not have exact same energy. They spin in opposite direction. So there is no way you will ever see this. You are violating the rule, which states that when 2 electrons occupy the same orbitals, they have opposite spin. We call this magnetic spin, and it is represented as m's of s. We call this m's of s, and it takes values either positive or negative, positive half or negative 1/2 to make it whole, to cancel out. Doesn't really matter. I know somebody, oh, let me just put that. Doesn't really matter which one faces where. It can be represented like that. Both this is correct and that is correct, so long as they do not spin in the same direction because of the spin quantum number. It's gonna help us, or where we are heading with this is writing the electron configuration. So we have looked at four quantum numbers which represent, or we use to represent, an electron. Somebody just came up with a principle we call Pauli's exclusion principle, which states that no two electrons in an atom have all four quantum numbers, that is N, that is L, that is M and S, having the same four quantum numbers, the same. N, L, and M's of L could be the same, but M's of S could change, could be negative. All right. This means the last value here for M's of S, that is the spin quantum number, should be different. So this is violation of Pauli's exclusion principle. Having what? Having two electrons facing the same direction is violation of Pauli's exclusion principle. When they occupy the same orbital, they should have opposite spin. So remember that when two electrons occupy the same orbital, they must have opposite spin, face in different direction as per Pauli's exclusion principle. Now, the main objective for chapter 6 is electronic structure. And electronic structure is simply writing the electron configuration of elements. And what is electron configuration? Electron configuration is proper distribution of electron in an atom. Does not mean that sodium number 11, all right, all 11 electrons are just anywhere in the atom. There is a proper arrangement of electron. We call this electron configuration. And there are three methods of writing electron configuration. How electrons are distributed around the nucleus of an atom is called electron configuration. Remember, there are three, and you should be rounded with all those three, because question can come from any, but it's just the same thing. It's not going to change. But there is one which is the foundation of the other two. You need to understand the first one, the main one, and the other two will just be built on the main one. And I'm going to show you the main one. You don't need to, memorize the electron configuration of each element on the periodic table. No. You do not need to. It's just like telling you, all right, memorize the atomic masses of element on the periodic table. No, you don't need to memorize those. So long as you know the concept, that's fine. I will show you a template on how to write the electron configuration for the main one, so that the next two methods will be much easier. And here is what you need to practice. Some of you already know. If not, I'll show you how to write the electron configuration. This is the template. This is energy level 1, 1s. Let's say this is the nucleus right here. Energy level 2, we have two sub-levels. Remember what I said earlier on. The superscript numbers stand for the maximum number of electrons. Superscript numbers stand for the maximum number of electrons which can go in there. And then there is 3s2, 3p6, and 3d10 maximum. I'm starting with 1s2, and then there is 2s2, 2p6, energy level 1, energy level 2, energy level 3. So when I come here, it will be 4. I should have just have it properly aligned. 4s2, 4p6, 4d10, and 4f14. There is a pattern here. If you look at 2 plus 4 is 6. So 2 plus 4 is 6. 4 plus 6 is 10. 10 plus 4 is 14. So when I get to 5, it's 2, 5p6, 5d10, 5f14, and then it's gonna go on and on and on. And then there is 6s2, 6p what? 6p6, 6d10, 6f14. No. And then there is 7. This is 7. All right. 7s2, 7p6, 56, 7d10, 7f14. Oh, I didn't mean to do that. So this is the general template for writing electron configuration. Writing electron configuration. You need to learn how to generate this template for writing electron configuration. This is energy level 1, energy level 2, energy level 3, energy level 4, energy level 5, energy level 6, energy level 7. N equals to 7. And if you look at the number of subshell, the number of subshell corresponds to the shell number. So shell number 2, I have 2 subshells. Shell number 3, I have 3 subshells. Shell number 4, 4 subshells. Shell number 6, and I have 6, and that's why I'm using dot here, that I should end up with 6. 5. I should end up with 6. I should end up with 7. I know you can practice this until you get it. Now, electrons occupy the subshells or orbitals according to increase in energy, all right? According to increase in energy. And in order to arrange the subshells according to increase in energy, you have to draw a pattern here. Look at the pattern, how I'm going to join the subshell. There is a pattern here. This is by itself. There is a diagonal, there is a diagonal arrow across the first 2 subshells. There is a pattern. I'm just gonna join 1, 1. It's by itself. Then when I come to the second pattern, I'm just gonna join the 2 subshells and then the 2 subshells. When I get to 3, I'm gonna join 3. I'm gonna call 3 times. And then I'm going to call 4 times. If I add 4, and then I'll go with a 4 times. So here I started with 1, 1. I'm just by itself, and then 2 here, 2 subshells close together, and then 3 of them, all right, and then 4 of them, and I'm writing 4, but I didn't have time space here. If I go to 8 and so forth, that is when you know, we don't even need to go beyond that. This should be enough for you to see the electron configuration. So if here is the end, I want to end in right here. I want to end in right here. This is where we want to end like that. Let's start from here. Without lifting your hand, you have to join the head and the tail of the arrow, 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 without lifting what? Without lifting your pencil, your hand off the paper, uh, go back again, then you come and then go back again. This pattern here helps you in laying down the energy levels, all right, how the electrons are distributed within the atom, or how electrons are arranged around the nucleus of an atom. So if I write as a straight line, I'll say this 1s2, and the superscript stand for the maximum number. Sorry about that. Let me just get these out of the way. 1s2, 2s2, 2p6. What I'm doing is I say 1s2 here, 1s2, and then go back 2s2, and then I go back to 3p2, no, 3p6, and then 3s2. So this is going to be 3s2, 3p6. After 3s2 here, you see 3s2. After 3s2, we go to 3p6. After 3p6, after 3p6 here, we go to 4s2. Look at this, 4s2. Let me just use a different color here. And then you go to 3. This is what we are talking about as overlap. You don't get to 3dp4, you get to 4s. You see this? Based on this pattern right here, after the 3p, you come to 4s, and then you go to 3d again, and then you come to 4p6. This is 4p6. And then after 4p6, right here, 3d 4p6 is 5s2, 5s2. And then after 5s2 here, you go to 4d10, all right, 4d10. And then after 4d10 is what? 4d10 is 5p6. So here is 5p6. And then after 5p6 is what? 6s2. So this is 6s2. And then after 6s2 is what? After 6s2 is 4f14. So here is 4f14. After 4f14 is 5d10. So this is 5d10. And then after 5d10 is 6p what? 6p6. And then lastly 7s2. 7s2. This is the arrangement of subshells according to increase in energy. You don't need to memorize the pattern I just generated from here. If you can remember how to construct this, then it's gonna be very easy for you to write the electron configuration. Remember, the superscript numbers stand for the possible maximum number of electrons, not the exact. For example, if you are asked to write the electron configuration for hydrogen, for example, this will be atomic number 1, and it's gonna be 1s1. That's why you write that. For helium, it is 1s2. You reconcile the atomic number with the subscript numbers. You have to add the subscript numbers here. You have to add the subscript numbers here until it adds up to the atomic number of particular element on the periodic table. Let's see. Oxygen, for example, is what? Oxygen is number 8. Is it number 8? All right. So this is 1s2. How many do I still? 6. 2s2. How many do I still need to get to 8? 4. And then 2p what? 2p4. I need 4. I didn't need to use all the 6 here. I don't need to use all the 6 here, because if I use all the 6, it will give me atomic number 10. 4 plus 6 is 10. That's how you write electron configuration of an element. If I want sodium, number 11, Na, this is number 11. 1s2, I still need 9. 2s2, 2p6, that is 10. And then 3s1, I need 1 to make 11. If you add everything here, it will add up to 10. So that's how you write electron configuration of electron configuration of element. Before I show you any other example, do you understand what is going on with this pattern right here? Are you able to generate? If not, you've got to practice. I've seen students making mistake that they don't know what, they just jump or they connect, or, how they overlap. If you look at this pattern here, there is an overlap. You get to, 4P before 4P comes before 5S, and 6S comes before 4P and 5D and so forth. It's because of the energy level. As the atomic number gets higher and higher, there is high chance of overlapping. It's gonna take a while, and then you come back again to a lower number in terms of energy level. This has to do with energy level. That's how you write electron configuration of any element. This is a neutral. And you may not see this. You may not see this in the text, but I'm just giving you a review of what you learned earlier on in Introduction to Chemistry, all right? This was Introduction to Chemistry, and this is what we call just ground state. What I just show you is the ground state electron configuration of element, showing the arrangement of sublevels according to increase in energy. All right. The number indicates the energy level. The letter designate the sublevel, the node in the orbital. All right. Superscript indicates the electrons of the orbital. The superscript numbers here. Superscript numbers here indicates the orbitals. I mean electrons. We can go in here. So 4p5, energy level 4, all right, maximum number of electrons, there are 5. This is just a designation what these numbers mean. Any question on, this is method 1 right here. Remember I said there are 3 methods. Method 2 here is simply knowing, all right. Method 2 is just using the, you have to know the first one in order to write the orbital filling diagram, where box represent electron and arrows, box represent orbital. This is orbital where the electron occupy. And this one represent electron. In orbital filling diagram, you use arrows and boxes or sometimes lines. You will see either this hydrogen, you may see this one represented like that, or all right, it's just, or a box with an arrow. Helium, one, it could be 2 arrows pointing in different direction, or a box with 2 electrons. Boron, 3, this is 1s, I have this. It's just the same, but or you may see this pointing in the direction. So we have what? Boxes for orbitals and arrows representing electrons. In terms of boxes, how they are arranged, it follows the same pattern as we saw here, as we saw in this arrangement. So this will have a box, this will have a box, this will have three boxes for 2p, all right? 2p will have this one, two, three, or 2p, you may see three boxes like that because there are three orbitals. There are three orbitals. I want to stop here today. All right. We will pick up from here next lecture. We will start from orbital filling diagram for electron configuration. Please learn how to generate that table. Review again. I want you to understand how to write the electron configuration. Remember, I said there are three. The first one is the main one. You have to understand the first one before you, and I'll show you the other method on Thursday. The class is dismissed. If there is no other question, I will stop sharing the screen. Thank you for joining in today. If you have any question, you can email me. Thank you, Christian. Thank you, Aaron. Thank you, everybody. Ken, thank you. Alfonso, thank you. Appreciate it. Be safe, sanitize. I'll see you on Thursday. The class is dismissed.